So when looking at half-life, before we get started, I want us to think about if I divide a number in half, then divide the answer in half again, and continue to divide each answer by half, will I ever reach 0? If you think about this, is it impossible or possible to reach 0? Well, if you divide everything by half, it almost becomes an asymptotic relationship that you will approach a value of 0, but never actually cross that threshold of being 0. So when we look at half-lives, half-life is the time it takes to lose half of your mass. Each isotope has a specific mode and rate of decay. We can see that on table N, and as we look at table N, you can actually determine the time it takes to lose half of your mass. So the rate of decay is called the half-life. Half-life is a constant and is never changed. So literature values on table N show you all those half-lives. And if you look over here, you can see the half-lives of particular nucleides over extended periods of time. So you can see, if we're looking at this particular series, you can see uranium's half-life is 4.47 billion years. It takes quite a bit of time. But you could see something like polonium, 214, has a half-life of 0.000164 seconds. So we can be very long half-lives or very, very short half-lives. Looking at a half-life, again, you're looking at the time required for the amount of radioactive material to decrease by half. So looking at this graph here, if I started with a ratio of 20 to 0, after one half-life, I am now at 10 to 10. So now looking at this, taking half of my product, or my considered parent atoms, I cut them in half, giving me 5. And again, I cut them in half to give me 2.5, and so on and so forth. Again, creating that asymptotic relationship of that of 0, but never actually crossing that threshold. So we call the original starting pieces parent atoms, and as in real life, parents produce offspring, in which we call daughter atoms. Not to be gender specific, we just terminology used. Instead of son atoms, we just call them daughter atoms. So we go from a 20 to 0 to a 10 to 10 to a 5 to 15 to a 2.5 to 7.5, and so on and so forth. So when we look at half-lives in this example, rubidium-87 undergoes a beta decay in the following reaction. The half-life of rubidium-87 is 60 billion years. So after the first 60 billion years, you can see that I went from having 8 squares to only 4 squares. So 4 parent, 4 daughter. Then after 120 billion years, I now have 2 parent and 6 daughter. After 180 billion years, I have 1 parent and 7 daughters, and so on and so forth. So looking at that, what you're looking at is the half-life, your starting amount versus your ending amount, and the time elapsed over that period of time. So first thing is we divide time, not grams. This is not a grams over grams. We're always focusing on time. The formula that we use for half-life is the number of half-life periods is equal to the total time divided by the half-life duration. So how much time took place in this specific question, and what is the half-life given to you either in the question or found on table N. Looking at a sample problem. The half-life of mercury-195 is 31 hours. If you start with a sample of 5 grams of pure mercury-195, how much will still be present after 93 hours? Big focus point here is the total amount of time, the duration of the half-life, which was given to us nicely in the question, didn't have to look at table N. So I take my total time, 93 hours, I divide it by my half-life duration, and I know that I went through 3 half-life periods. So if I started with 5, I go through half-life 1 and I end up with 2.5. Then I go through half-life number 2 and I end up with 1.25. And then I go through half-life number 3 and I end up with 0.625 grams as my final answer. So you're applying your half-lives, and as you can see here, I have half-life 1, half-life 2, and then finally half-life 3, giving me my overall reaction or amount of 0.625 grams. Looking at practice problem number 2, I have gold 191, which has a half-life of 12.4 hours. What mass of this isotope would be left after 49.6 hours if you started with 7.50 milligrams sample of pure gold 191? So first thing, as I'm given my total time, I'm actually given my half-life duration, so total divided by half, so 49.6 divided by 12.4 gives me 4 half-life periods. So I go through half-life number 1, and I go to 3.75. I go through half-life number 2, and I have 1.875. Then I go to half-life number 3, and then half-life number 4, giving me a total amount of 0.46875 milligrams of gold 191. Problem number 3, given that the half-life of carbon-14 is 5,715 years, consider a sample of fossilized wood when alive would have contained 24 grams of carbon-14 and now only contains 1.5 grams of carbon-14. How old is the sample? So in order to solve this question, you actually have to work backwards. Looking at this and working backwards from this given question is that we actually start with 24 grams. And I apologize for this little typo here. This should be 24 grams. So I start with 24 grams. And 24 grams is then broken down to 12 grams, which is then in half to 6, which is in half to 3, which is in half to 1.5. So I started with 24 and I ended with 1.5. So you have to figure out how many half-lives took place in those amounts. Well, the easiest way to do this is take 24 and divide it by half on your calculator, and you know that that's 12. Divide it by half again. There's 6. Divided by half again, and you have 3. And you divide it by half again, and you end up with 1.5. By doing this on your calculator, you now know that 4 half-lives have occurred. Thus, you can plug in x for your unknown, so your unknown being the total amount of time, into the formula we talked about prior, and solve for x. So I have 4 times 5,715 years. Solving for x gives me 22,860 years. I started with 24 grams and ended with 1.5. With carbon-14, it would take you 22,860 years to do so. Practice problem number 4. We're looking at iron-61. As we look at iron-61, it has a half-life of 6 minutes. How much of a 100-gram sample will remain after 18 minutes? So total time divided by half-life duration gives me 3 half-life. So I take 100 and divide it by a half, divided by a half, and divided by a half, leaving me with 12.5 grams. Last practice problem. How many years did it take for a 2-gram sample of carbon-14 to decay to 0.0625? So carbon-14, I don't know the half-life, so I'm going to look at table N, and table N tells me the half-life is 5,715 years. So in order to determine how many total amount of time has gone past, I must figure out if I started with 2 grams and ended with 0.0625 grams, how many half-lives took place. So I take 2 and I divide it by a half, and then I divide it by a half, and then by a half, and a half, and a half, until I get that final amount that I want, and I figured out that, oh, 5 half-lives have occurred. 1, 2, 3, 4, 5. I had to divide it by 2 5 times on my calculator. So, again, solving it into our expression, we know that x is our total number of times, so 5 times 5,715 years gives me a total of 28,575 years. So, looking at those questions, those are half-life questions. 2 different ways to solve half-life problems. I can either give you the half-life and the total amount of time, and you can tell me the amount remaining, or I can give you the starting amount and the ending amount, and you tell me how much time it took place to get from the beginning to the end. 2 different ways to tackle these different types of problems, but very effective methods.